In active mountain belts, erosion works across a wide range of timescales and through diverse processes. We need multiple tools to measure how fast landscapes are wearing down. In this lesson, we will build an intuitive picture of three complementary methods: low-temperature thermochronology, cosmogenic nuclide dating, and sediment flux analysis. Each method has its own time window and type of data, but together they give a powerful multi-scale view of denudation. First, low-temperature thermochronology. Imagine a mountain cross-section. As erosion removes material, rocks move upward, cooling as they pass through closure temperatures roughly between 60 and 300 degrees Celsius. Minerals record the time since they cooled below those thresholds. By sampling different elevations along a vertical profile, we infer how fast rocks are being exhumed, which often approximates the erosion rate. Over millions of years, thermochronology typically reveals rates on the order of 0.1 to 1 millimeter per year, and even several millimeters per year in extremely active zones. Next, cosmogenic nuclides. Cosmic rays strike mineral surfaces and create rare isotopes like beryllium-10 in quartz. The amount that accumulates depends on how long and how close to the surface the grains have been, and therefore on the erosion rate. Basin-wide erosion can be measured by sampling stream sediment, which mixes grains from across the catchment. This method typically integrates over 1,000 to 100,000 years, smoothing year-to-year variability but remaining sensitive to millennial scale changes. Under steady conditions, faster erosion means lower concentration, and slower erosion means higher concentration. Finally, sediment flux analysis. Treat the river as a natural conveyor belt. Measure the sediment load over time, divide by drainage area and density, and you obtain an erosion or denudation rate. This method captures years to decades, even individual storm responses. The key conversion is erosion equals sediment discharge over density and area. For example, 1,000 tons per square kilometer per year corresponds to about 0.37 millimeters per year, assuming rock density of 2.7 grams per cubic centimeter. Now let's compare and combine. Each method views denudation through a different temporal lens. Thermochronology gives a deep time average. Cosmogenic nuclides give millennial scale averages. Sediment flux gives modern, high-resolution rates. When these agree, we gain confidence that modern erosion is consistent with Holocene and geologic averages. For example, a mountain belt might show 1 millimeter per year from thermochronology, 1.5 from cosmogenic beryllium-10, and 2 from sediment flux. That set suggests steady to slightly increasing erosion and highlights how integrating methods yields a more complete picture of orogenic denudation. To summarize, no single method tells the whole story, but together they reveal the multi-scale dynamics of erosion in mountain belts. Use the right tool for the time window, and always compare across methods to detect transients or human impacts.